Drum roll, please, everyone. Where are we at? 16 out of 23. So, yes, nag your friends. And in all fairness, the reason that I want everyone to do this is not just to get the point of extra credit I'm offering as an incentive, but because I actually genuinely want your feedback. And I'm asking you to spend time out of class to give me the feedback. It seems fair to compensate you for the time that you've spent. So that's my official rationale. I do value your feedback. I do try to make changes when I can, not always possible. For instance, one of the things that folks frequently ask for is the ability to do more group work kinds of stuff. The problem, though, is that I can't do hybrid Zoom and group work at the same time when I don't know how many people are going to be showing up in either modality, and I can't walk around the room and talk to people and sit here and talk to the Zoom rooms at the same time. So, like, that's an example of something that if I made everybody show up in person, we could do more of that kind of thing. But there's a lot of people who don't want to or can't show up in person, and so I'm falling on the side of that. But other kinds of ways to spend class doing different things, I'm always interested to get new ideas. So interestingly, the Qualtrics survey had more people responding to it the last I looked. So folks are doing that one. So don't forget about this one. It's due sooner on Saturday. All right, so then other things that are due, just to remind us what's going on. You should be working on homework 4 revisions if you want to do that. Homework 5/6/7 using SAS, Stata, or R. I'm encountering a few folks finding incorrect answers in the second decimal place, but they've done everything correctly. If you think you're in that position where, like, I'm pretty sure this is the right answer and I don't know why it's taking it, round up or down 0.01. And if that doesn't work, send me an email and I'll check your code. And if you got the right answer and it's just not taking it, I will give it to you. I'm not intending it to be a source of frustration. Unfortunately, the reality is that at this level of computing, subtle differences in which version of R or which operating system or all of that can combine to create slightly different numbers. So that's where the homework system starts to lose its ability to be effective when we get into increasingly complex levels. So it's good at the easier stuff, not so great at this stuff, but we're going to make it work. So those two things and anything else that needs to be done by next week. Office hours for 4 days, not on Friday, but otherwise, I'm available for individual meetings as well. So let me know if you need anything, okay? Okay, Zoomers? Oh, nice drum roll, I like that. Okay. All right then. What were we talking about last time? Here's a slide to help you remember. I'm in lecture 8, slide 8. What's this slide about?
Basically, you are like replicating for your x what you did for your y and dividing up the variance between like level 1 and level 2.
Yes, replicating for x what we did for y, letting the model divide up the variance for level 1 and level 2 rather than trying to do it with brute force observed variables. Yeah, that's the idea. So to be able to do a model like this, you need some kind of multivariate software. That can be done in what is known as multi-level structural equation modeling. Technically, you could do this in a regular structural equation modeling package, but for cluster data, it's very painful and tedious. I would not try to do that. For longitudinal data with relatively few occasions, that's a better approach, but not as much for this. We talked a little bit about this. Why would you want to do it this way?
I don't think this is the right answer, but it doesn't take out missing.
Yes, that is one of the right answers. How it addresses missing data. So because x is now an outcome within the likelihood function, meaning its mean, variance, and covariance with other things get found as part of the model, you can have missing cases on it under an assumption of missing at random. The downside to that, though, is that it requires you to make a distributional assumption about it, just like you would for y. So if x isn't normal, then you're going to run into problems. So this works best for continuous covariates. And then plus, you could tell it that it's binary or something, but it will yell at you if it's not actually an outcome. you might actually have to have something else predicted just to work around that situation, I have found. But missing data is one reason. What about boxes versus circles? So this is something we haven't really talked about in this class, but it's relevant in the context of measurement models and latent variables. If we make a cluster mean box, such as this version of the model here, we're assuming that this cluster mean is perfectly reliable. We're not paying attention to differences in the cluster size that might create differences in reliability. We're not paying attention to differences within cluster variance. By making a latent variable, that's supposed to be a more realistic version of it, where the level 1 part of the term that would normally be in the box is not in the circle. So do you remember in thinking about why reducing the level 1 residual variance makes the random intercept variance go up? Remember we were talking about that? Because they're tied together. Because the random intercept variance that you get in your model is not just cluster differences. It's cluster differences minus how much of those is expected by chance, where expected random fluctuation is indexed with residual variance divided by the level 1 sample size. So the model has less variance in it than would be observed because it's corrected for the expected contribution from level 1. By doing it this way on the X side, it gets corrected too. And so this between relationship, simulation research, some of which is on your reading list, has found that this relationship will be stronger when you're using a latent circle as the mean, or intercept as we're calling it, rather than the observed mean. So it's supposed to give you a better representation of the level 2 effect. So those would be the two reasons to do this. Since we're on here, let's just go to some pros and cons. This is slide 11. So cons first. No REML. Structural equation modeling software does not have REML estimation. And REML estimation, we haven't talked a lot about this in this class, but just to review, it accurately estimates variance components in small samples, small meaning the number of level 2, whereas ML versions are going to be too small. So if you have a relatively small number of clusters, you need REML, and that usually goes with the use of denominator degrees of freedom for the same reason. Otherwise, your results will look too optimistic. Standard errors will be too small, p-values will be too small, and there's some review papers about this that I've cited here that you can refer to for those. Another one we talked about at the very end, remember what's a circle and what's a box? Remember that? Because you didn't want to see my random slope model, so I did get that instead. Remember? Yeah. Vaguely, yeah. It's that point of the year where everything's just sort of, you know, it's flying through, but we're going to make it work. Because you know what? I'm recording. So at some point in the future, when you have more brain capacity, you can go watch it again. It's fine. We talked about interactions. So if I wanted to know if the between effect varied as a function of some other level 2 predictor, we could do that. But in multivariate land, when the interactions are among circles, that's a latent variable interaction. It's much harder to estimate. It requires numeric integration or Bayesian estimation, and so you'll be limited in practice by the number of interactions you could have in your model at the same time. And then the big one, what you get back can be tricky to figure out, whether it's between or contextual. So that's not so much a limitation because it can be figured out, but when you're first getting started with these techniques, it makes it harder to figure out what you have in front of you and what to do with it. So I keep citing my paper because this is one of the few sources that actually tried to map this out that I'm aware of. Why would you do it? Well, because you're treating X the same way you're treating Y, letting the model figure out the variances. Those should be better. You're not assuming that it's perfectly reliable. As I said just a second ago, level 2 effects are going to be stronger because they're going to be disattenuated for level 1 error. And here's some sources that show that in practice via simulation research. And it's also really the only way to do multi-level mediation. So the idea of whether a predictor operates on an outcome through some other variable. If you have multi-level data, let's say you have people in clusters, how many kinds of mediation do you think you could have? 1 or 2? Making this easy. 2, right? 2 levels, 2 kinds of mediation. What if you had 3 levels of data? How many kinds of mediation can you have? 3. And there's actually more than that. if you count random slopes. So random slope variances become additional level 2 variables that could be part of your mediation chain. So then there's a lot more. There's also, this is the only way to do location scale models in which the differences in variance are a predictor. I've got a slide about that in just a second. So here's mediation. Just a couple things about this. Let's say that I have a variable x is my predictor, and theoretically I think that x causes changes in m, which in turn causes changes in y, and so at least part of the reason why x and y were related is through m. That's the idea of mediation. And what level your variables are measured at in a multi-level sampling design logically dictates what is possible. So if I have only level 2, then I can only have level 2 mediation. And if you go through this list here, the only situation in which you can have 2 levels of mediation is if all 3 variables are measured at level 1. Otherwise, you can't. So let's say if I have this line right here, 1, 2, 2. How is it possible that x at level 1 can predict m that is measured only at level 2? Does that seem weird or does that seem plausible?
If that's the cluster mean, or something.
So x is a level 1 thing, m is only measured at level 2. It's a cluster characteristic, and y is only measured at level 2. So how is this logically possible that you could have mediation when things are at different levels like this? Say it louder.
Is it cross-level interaction?
You could have cross-level interactions, but that would not be necessary to make this work. Zoomers, any ideas? Roomers, any ideas?
Random slope?
Random slope. You could have one of those, but not necessary to make this work. Can I give you a hint? Trojan horse. Is this level 1 variable just a level 1 variable, or is it also probably level 2? Also probably level 2. So the way that this line in particular would work is that it is the level 2 cluster variance in x that would in turn predict the cluster variance in m that would in turn predict the cluster variance in y. That's how. So every level 1 variable also has level 2 in it. That level 2 part has a separate relationship than the level 1 part. Make sense?
I think so.
Think so. Or was that just a yawn?
No.
Okay, I thought it was a light bulb. You
So,
think? Yeah.
Lisa, just clarifying, so
Hit
they're
me.
related because of the clustering? Is that the idea?
That's the idea.
Okay.
So the one part here, the cluster variance at level 2 within this X predictor is what could be the initial step in this mediation chain. That's why this works. The only way that you could have a mediation chain happening at level 1 and level 2 simultaneously, though, is if they're all measured at level 1. And so it's the level 2 part of X that would predict the level 2 part of M that would predict the level 2 part of Y to make this a 2-level mediation. And what if you forgot about that and then just did this triangle on multi-level data? What have you done? Smushed. So can you have smushed direct effects and smushed indirect effects? Certainly you can. I know, right? It's like once you see it, you can't unsee it. Everything is a multi-level problem. That means that every kind of analysis you would do needs to be the multi-level version. Anyone going to take SEM with me next semester? A couple people are, if
Yep.
you haven't already. Woohoo! In that entire class, you are going to be allowed to completely ignore this because it's not a multi-level SEM class. But if you have multi-level survey data and you wanted to test the factor structure of it, the proper way to do that would have a between factor model and a within factor model for the same reasons. Otherwise, your factor loadings will be smushed. It's all the same. So even though we've focused on a fairly narrow context of regression in this class, it extends. The principles extend to any other kind of model that you might fit. Multi-level. But in that class, I'll let you pretend like you didn't have it because it's only fair. Maybe throw some cluster corrected standard errors at it at least, or something like that. You can do that easily. All right, random slopes is what I promised to show you. Can I show you that now? Okay, I know, I'm the worst. I keep teaching even though it's the last day of the semester. I know, but you'll get over it, right? Okay, good. So we did empty means random intercept. We did observed predictors and latent centered. We did not do number 3, as I remember. So let me get to that one. So model 3 is this version, essentially. So we have a cluster mean centered version on the slide. I'm going to switch that out to be latent centered, but otherwise the model will be set up the same, where we have a main effect of homework and mixed grade at level 2, a main effect of what is here the cluster mean that will become the latent intercept, and we're adding a random slope. But to do that requires a change in the syntax. Okay, 8A, that's the one I want. Okay, so I'm opening model 3 in the download packet for 8A, and I'm going to make it big so we can see it. So this is M+ code. It's a .inp file that runs it, and then what you have in front of you is .out as the output file, but the output files always repeat all the syntax at the top, so then the output file is the only thing that you really need. So you have to tell it the name of your data set as a text file. You have to tell it the names of your variables, what variables are going to go in your model. Otherwise, it will stick everything in your model and it will be all wrong and weird. In this example, we have an outcome of language. That's why. We have a predictor of student level verbal ability that should predict their language outcomes. So in the within model, this is level 1. Do you remember what it means if you list the name of a variable by yourself? In M+ code? We talked about this last time.
You get the variance.
That's its variance. Now, is it variance or residual variance? Yeah, see, this is the tricky part of the language. In the rest of the world, residual variance means leftover variance, like after you've predicted something. But in this class specifically, it is residual as in level 1. So you can end up with language having residual, like it's level 1 residual and it's leftover, whereas verbal is not being predicted by anything, so it's just one type of residual and all the variance. And yes, that's hella confusing, and I'm sorry, but these are the words that people use. Point being, this is level 1 within cluster variance in verbal that we're asking it to estimate. This is level 1 within cluster variance in language, and we're going to predict it from verbal. So to do that, with a random slope, I had to change the notation. I am creating a new, what is in terms of the program, latent variable. I have named it L1V slip, which to me is level 1 verbal slope. And why don't I put more letters in here? Nikki, why don't I put more letters in here?
Because variable names are limited to 8 characters.
Because you can only have 8 characters, because it's 1985 up in here. It's state-of-the-art modeling with 1985 technology. That's why you input a text data set with 8 characters. So that's why it has to be like slip and stuff, because you gotta economize. So in the notation for the model, we have our beta 1, right? And then beta 1 gets defined with a fixed effect and potentially a random effect at level 2. That is exactly what is happening. So I am essentially creating beta 1 right here. I didn't name it beta 1 because I don't hate you guys. I named it something that would be easier to keep track of. But I have in the comments here, that's what this is. So this is the name for the relationship defined right here of level 1 verbal predicting level 1 language. That name then in the between model picks up a mean and a variance. We would call this mean of this variable the within cluster slope, the fixed slope. So this starts to hurt a little bit. But if you think about it as beta 1, like the first thing that goes into beta 1 is the fixed slope, and then the variance around it is listed as a model parameter, along with the covariance between the random intercept and that random slope. So level 2 is where fixed and random slopes get defined, and you could then potentially predict them. So I'm once again asking for a contextual effect as the difference of the level 2 verbal intercept effect on language minus the level 1 verbal residual effect on language with the within. So that part is the same. The only catch is that these are not variables that are observed, they're variables that are being defined in the model. So verbal 10 in the level 2 model refers to its random intercept, just same way that language in the level 2 model refers to its random intercept. Verbal 10 in the within model refers to its residual the same way that it does for language. Okay, so there's a little bit of like, I don't know how to describe it, rearrangement, different words and different ways of thinking it, but it is the same, I promise. You believe me? Yeah, like why would I lie? I rarely lie. Sometimes I oversimplify on purpose, but I rarely lie about this kind of stuff. So we go through, scroll, 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 and then we get down to new terms here. So let's try to guess what these things are. Here's my estimate. Here's my standard errors. Within level, okay? Are these people things or cluster things? People things, all right. The within level variance for verbal 10, what is that? What would we call it?
Random slow variance.
Not on the within level, but good guess. This is not a parameter that you would normally have in what we've done so far, because X does not have its variances estimated as part of the model. It does now, though. So this is a new term that you would not normally see. This is level 1 residual variance in verbal. So this is the analog to, let me go back. It's this circle right here. If I were doing this using standard mixed model stuff, what is the observed version, variable version this corresponds to? How would I make this same idea out of an observed variable?
Subtract out the cluster means or use the constant syndrome.
Yep, this version in particular is the subtract off the cluster means version. So the analog is this. Level 1x minus the cluster mean is the observed variable version of what the model is now estimating directly as level 1 residual variance for x. It's the same idea. It's just that we never estimate the variance of predictors as part of the model. Like, that's not a thing. But according to the model, this is not a predictor, it's an outcome. And it's a multivariate model, meaning that outcomes can predict other outcomes. So this is something we would not normally get, because this is x. Language is y. This is something we would normally get. What would you call this 39 in the words that we know?
Residual variance or regular residual.
Yes, level 1 residual variance, and because it's being predicted by verbal, it is also leftover level 1 residual variance. So residual, residual. I know. So this is all that's in the within model, because everything else is up in the level 2 model, in the same way that it is when you write, nope, wrong PowerPoint, the equation. All the fixed and random effects are up here in level 2, with the exception of E. So it's the same way in this setup. So between level. Between is people things or cluster things? Cluster things, all right. So we have the amount of homework a school uses on average, whether the school uses mixed grades, predicting language, and then verbal 10. So this is the level 2 between slope. between the random intercept for verbal and the random intercept for language. It's actually stronger than what we found in the results for this model. The model gave us 3.6 when we were using the cluster mean. I got 4 something. So the pattern that I expected to hold did. You get a stronger relationship after you correct for the part of level 1 variance that shouldn't be there. Level 1 slip with language, that's my random intercept and random slope covariance. Means of verbal 10, this is the fixed intercept for x. In the same way that y gets 1, x gets 1 too. The mean of this thing, what on earth do you think that number refers to? 2.4 is the mean of level 1V slip. It's totally not obvious. Any guesses? Let me go back to the equation. This is the mean of beta 1. What do we call it? What would we call this normally?
It's still within effect.
Yeah, it's a fixed slope. It's the within slope specifically. From the way that M plus is viewing it is that beta 1 is a variable. It is a variable that represents how verbal predicts language, but it is a variable. And this variable has a mean and it has a variance. The random slope is the variance part. The fixed slope is the mean part. I know, it's weird. But that's how it is parameterized. That number is very close to what we got out of the observed data, which is always the case for level 1 slopes, or most of the time. Then we get into intercepts. That's my fixed intercept for language. We do have those normally. The variance of level 1 V slope. Now, what's that one?
That's the random slope variance.
That's the random
I know.
slope variance. The variance of the slope. That's a little bit clearer than the other one. And this is the variance of the X random intercept for verbal, which is not normally there. And then this residual variance means leftover, because we're in the between model. So this is leftover random intercept variance right here. That's what that means. Good times? No, not good times. Okay. We hate this, don't we? You don't have to do it.
Lisa, what do you mean by leftover random intercept variance?
I mean that language is being predicted by 3 things right now.
I see.
So
Okay.
this is like U variance left over after controlling for those 3 things. And that's what it means when it says residual in this context. It means left over. I'm going to skip the next 2. They do interaction terms because those are crazy convoluted. But if you ever need to do that, here's some examples. Can I talk about location scale? Why not? I have a slide on it. Yeah, there we go. Okay. So up to this point, in everything that we've done, we have made a really critical assumption that I barely even talked about. How many different within cluster variances would we have in our model for an outcome?
Just one.
1. So what are we saying about how people differ from each other in their cluster?
The same.
They all differ to the same extent. So if you think about that within the context of a school, this assumption means all schools are equally variable with respect to their students. In the context of an organization, like what if, I don't know, there are something like course evaluations where individual students are nested within instructors, hypothetically speaking. Hypothetically speaking. So the results that I will get back on Christmas Eve, mind you, that's when they're coming, just in time.
Merry Christmas.
Merry Christmas, your students hate you. Those results give me the mean, right? They give me the average of all your numbers, but they also give me standard deviation. And that is usually the more interesting number. Because there are two ways to get like a middle score, right? Everybody thinks you're meh, or some people love you and some people hate you. Do you think those are the same classrooms? Where everybody's meh versus polarizing? Probably not. So if you think about this in the context of clustering where, like, if you're rating your supervisor or your instructor, one way to think about within cluster variance in that context is unreliability or noise. Another is to think, oh, maybe there's a signal here. Maybe some supervisors are more polarizing than others. Maybe some instructors are more polarizing than others. So in certain kinds of sampling designs where the people are providing information about their cluster, people could reasonably disagree with each other. And we can model that. So it's called a location scale mixed effects model. Got a couple articles on your reading list that talk about this. The idea is that we're going to take level 1 residual variance, which previously we were saying was one number, constant across all the clusters, and we're going to see if it varies. If the variance varies. No, I'm not making this shit up. It's a real thing, I promise.
I believe you.
Yeah.
English is,
So
the expression of it.
it will go better if you come up with another word. So in the context of, I would say we could call it disagreement or discord or something like that. Can you think of another word that would mean that? Inconsistency. I like that one. So to what extent are responses to the same target inconsistent across people providing the responses? Some targets might have greater inconsistency than others. Okay, that's varying variances. So we can predict it. So we can end up with something that is called a scale model in addition to the location model, which is what you call a multi-level model. Okay, so location, scale, multi-level models. Location is the part you know already. The scale part adds this idea of differing variances across clusters, and they can be characterized by a random scale or fixed cluster predictors. A random scale, and I know this is going to hurt, is a random intercept for the level 1 residual variance. It's the idea that each cluster could need their own amount of disagreement, their own estimate of the extent of inconsistency of that cluster's set of responses. And we're predicting it, rather than predicting the variance directly, we are predicting the log of the variance. Crossover, why would we do that? Cough, cough, generalized modeling concept.
Well, Lisa, I actually wanted to ask about this specifically.
Okay, 1 second, Nathan. What was the
Okay,
answer?
okay.
Like the distribution, like it's probably not necessarily a normal distribution.
Yeah, variances do not have normal distributions,
So you would
usually.
probably need to adjust for that.
You need to adjust for that.
You can't have zero. Well, I mean, I guess you can.
No, can you have 0? Like,
And not in real data, I
no,
guess.
probably not. Can you have negative variances?
No.
So is there like a boundary problem to this thing, maybe? And how do we solve boundary problems? Link functions. Yeah, log link function, that's why. Okay, Nathan, hit me with your question.
So, is the foundations of location scale models, is there an assumption that everything comes from a standard normal distribution and link functions are applied to get to the values that we need within the bounds that we need?
Yes.
Okay, thank you.
Yep. Yeah, the random scale is assumed to be normal. And so the link function here creates a linear predictor that the log function that ensures stays above 0. That's why. No, not yet. So in M+, I gave you a model with this. let's do 6B real quick. And I'll show you how easy this is to do. This is way, way harder to do in any other software package. This is the easiest way that I've ever seen. The person who made up these models, by the way, is Don Hedeker. He has written his own software package to do this as well. But in his software package, these differences and variances can only be outcomes. They can't be predictors. So like if you had a hypothesis that the extent to which your students disagree about your teaching goes and predicts some other thing, then you would need to do it this way, or code your own in Bayes. So M+ starting in version 8 introduced this thing right here called log V. That is a keyword that it understands, stands for log of the variance, I'm guessing. So if you do this at level 1, so I'm saying log V language, meaning I would like to take this residual variance for language and turn it into a thing to be predicted, a new latent variable in the model. Then down here, you can refer to log V as the random variance in the unreliability across clusters. You can then correlate it with the other random effects, and then you can then predict it. So maybe one of the reasons why some schools have more variance across their kids is whether they use mixed grades or not, right? If they're different grades, maybe they have more variance. So you would think about reasons why you would have differential agreement or disagreement, and you can test the reasons in the model. That's what these models are for, and they're super cool. Down here, I am EXPing the results to put them back onto the original scale of the variance rather than the log scale. So a little bit of tour of that. So this is a cool thing, but that was one of the topics I didn't have time for. There, now you've seen it before. And you have some readings you can do if you want to know more about it. All right. Want to hear a little bit about 3-level models?
Yes, please.
Yes, please. Charlotte says, I'm doing this for my homework and you didn't teach me. But I did give you resources. So how do you know what kind of 3-level model you need? The answer is your outcome, not your predictors. Well, that's the thing that people get confused by. So if I have, for instance, students nested in schools and schools are nested in districts, if I'm studying student outcomes, like whether or not an individual student eventually graduated high school, that requires a 3-level model. If I were interested in school-level outcomes, such as graduation rate, that's still only a 2-level model. Because the outcome has school variance and district variance. If I then wanted to use any kind of student predictor to explain why some schools have higher graduation rates than others, the only way that I would be able to do that is to aggregate across students up to the school level, because there's no student outcome to be predicted in that case. So like the mean whatever of the students could predict school's graduation rate, or the range, doesn't have to be the mean, could be the variance even. Differences across students could predict something. What kind of nesting or crossing you have, what your levels are, depends on the sampling design. So here's a couple examples of where it would get weird. Let's say that I'm measuring multiple people within multiple countries over multiple years. If it's the same people over time, and they live in the same country over time, then level 1 is what year it is, level 2 is person, and level 3 is country. Okay, but what if it's the same countries over time, but every year they recruited a different sample of respondents? Oh, I've seen this in political science. They do this kind of stuff. When I taught for ICPSR, several people had this type of design. Time is level 2. People within a year, but years are nested in countries if you believe that your representative sampling holds so that you're really measuring the same country over time. That's a belief. I had a student take my longitudinal class, here's the last example, and they had a design that was more like this, where people were nested in countries, but then every year they went and got a whole new set of them.
A whole new set of countries and
Yep,
people?
everything.
Okay.
Years at the top. And this person went through my whole class, and at the end I was like, yeah, you realize you don't have longitudinal data, right? This is not longitudinal. If you haven't measured the same thing repeatedly, it is not longitudinal. What you have is just chunks, like you just have cohorts of years. So you really have to think carefully about how people and groups are measured to figure out what the levels are. Time is not necessarily level 1. It only is if everything is repeated across people and countries. Here's some notation. The multi-level placeholder notation on steroids. Let's say that I have teachers within schools within districts. So YTSD starts out the same, except for the 3, right? We have our random intercept placeholder. We got our E. So this would be how far off the teacher is from the school's random intercept. I come to level 2 here. Here's my school random intercept. It starts off with another placeholder. So this is delta, I believe, and it has its own definition at level 3. So level 3 is where the fixed intercept is, plus how far off the level 3 cluster is from that, which is district. Those feed into here. Then we pick up how far off your school is from your district mean. Those feed into here, and then we pick up how far off your teacher is from your school's mean. So the composite notation is much easier to understand. Fixed intercept plus level 3 random intercept plus level 2 random intercept plus level 1 residual. And my bad for reusing V, because I needed another letter. And you know what comes after U? V, right? I was like, well, if level 2 is U, then level 3 should be V, right? And then someone was like, hey, isn't that like V matrix? Like in the, oh crap, I reused V. So yeah, when I fix my book, I got to find another letter. But so, this is not the same V that we've talked about in that context. But yeah, the idea though is just the same as in 2-level models, but you just have another level. Why is it some districts have different outcomes? I don't know, but here's the variance for it. Why is it that within a district, some schools have different outcomes from each other? I don't know. Here's your random intercept at 2 for that. Within a school, why is it that some teachers have different outcomes than others? I don't know. Here's your level 1. So there's 3 different kinds of variance. How many pseudo R-squares would there be in this model?
Two.
I got to vote for 2.
I would say 3
Got to vote for 3.
at least.
How many pseudo R-squares are possible? Pseudo R-squares are what, Mo? You did the ChatGPT assignment? Would you like to phone a friend?
Yeah.
Okay, who do you want to phone? Any other people do the ChatGPT assignment who are here? There was a question on there about pseudo R-square. What's it mean?
I'm revising and saying 3.
Okay, he's picking 3. 3? We're converging onto 3. 3 is correct. Pseudo R-square is per pile, per variance component. Of the level 1 reasons why teachers differ from each other, how much did you explain? Of the level 2 reasons why schools differ from each other, how much did you explain? Of the level 3 reasons why districts differ from each other, how much did you explain? 3. How many total R-squares would there be?
1.
1, because that's why we call it total. Total R-square is all the fixed effects working together across levels to say how much Y variance we explained. So total R-square is compute the predicted Y based on the fixed effects only, correlate that predicted Y with the real one, that's R, square it to become R-square. It's the exact same way that it's computed in multiple regression. So that gives you an overall, how well did my model do, like omnibus statement, that is complementary to how well is my level 1 model specified, my level 2, and my level 3. Question, if the outcome of the 3-level model is Bernoulli, would there only be 2 since then there's no level 1 variance estimated? Oh, good question.
It's still there, you just don't estimate it.
That's right, it's still there. If I have the world's best logistic model, what is my variance left over?
I squared over 3.
Yep, 3.29 pi squared over 3. If I have the world's worst logistic model, what's my variance? The same damn thing. So you can't do pseudo R-square on that. So in that context, yes, there's only 2 levels worth that could be computed, but there is still error at level 3. Pictures? How about this? So once upon a time, there was an E. Why does it say within person? Damn it, that's my other class. There, fix it. And I always update the slides afterwards, by the way, whenever I catch something like this, so I'll fix that. Okay, once upon a time, there was an E. So this is all the variability in some outcome. First thing we do, split it into 1 versus 2. So I'm in the example of teachers within schools within districts, okay? So the first question we answer is, how much of the variation is due to clustering, right? And the proportion of variance due to clustering has a special name, ICC. But this now has a revised name, ICC level 2. So ICC level 2 is what proportion of total variance is at levels 2 and above, is due to teachers being clustered within schools. And if they're in schools, they're in districts too, like they're tied together. Is that it? No. There's a whole lot of blankness over here that we got to fill in. So a 3-level model then would then take level 2, because right now this is 2 and 3, and split it like that. So there's another interclass correlation that would be relevant to compute. Once you've isolated the variance due to clustering, so schools and districts, how much of the school variance is actually level 3 at districts? And how much of it is within districts at level 2? So I call that ICC level 3, because this ICC tests whether you need a 3-level model or whether a 2-level model would be enough. So these are the 2 ICCs that I think are most useful to describe what happens in a study. Do you think ICC level 3 is given by any of the stats programs that you know? No, it isn't. Do they give you something called ICC level 3? Yes, they do, but it's not this one. Because, right, that'd be too fun. What it is of the total variance, how much is at level 3? That's what they give you. That's less helpful. That's just a straight proportion. So in 3-level designs, you will have to work a little bit harder for your reader to follow what your ICCs mean, because there are different permutations of them. So I like this one because it answers the question, how much clustering is there at level 3 out of level 2, in the same way that we initially answered, how much clustering is there at 2 out of 1. Okay, yeah. So here's the formulas then to go with those ideas. ICC level 2 is the one that you know. Of the total people variance, how much of it is due to schools? And if it's due to schools, it's due to districts too. That's why you have both of those terms in the numerator. And the denominator is the total. What ICC level 3 is doing is taking this numerator and splitting it. So of the school variance, specifically, ignoring the people, how much of that is between districts? That's ICC level 3. So that's where we're at here. What about random effects? Can we have random slopes in 3-level models? Sure we can. So let's say that I add some person level predictor. It accounts for some of the level 1 residual variance. If I wanted to add a random slope for that person predictor, that splits what used to be level 1 residual into a new level 2 variance called the random slope. And then we have deviance around those random slopes as the level 1 residual still. So this is this much we've done this semester. Am I done? Probably not, no. Because guess what? This slope variance could have clustering in it too. Crap, I know. No, the Zoomers say. I know. Watch. Don't believe me? Just watch. School slope variance gets split into how much of it is because of what district you're in. There's commonality potentially in the random slopes at level 2 across level 3. So then I have 2 different slope variances. So all told, my model would look like this at this point. I have level 1 residual. I have school intercept and school random slope. Those two would have a correlation because they are both school things. I would have level 3 district intercept variance and level 3 district slope variance, and they would have a covariance because they're both district things. Now, how many pseudo R-squares do I have? The things in boxes are the final result. How many different types of variance do I have? 5. 5. Yep. 5 of them. Which of these could be predicted by district characteristics? What color? The green ones. So a main effect of a district characteristic would predict the intercept. An interaction cross-level of a district characteristic with the variable the random slope is for would predict this green circle right here. So people X interacting with district whatever would explain the district random slope of people X as the predictor. Which circles could be predicted by school things? Yeah, aqua, I don't know, teal, cyan. Okay, I think we voted on this before. We landed on cyan, yeah. So school things, as main effects, predict school random intercept variance. School thing interactions with whatever variable the random slope is for would predict this box. And what predicts the blue one, the dark blue one? People things, teacher things, yep. Or interactions among teacher things. Am I done? There's one more thing I could put in here. How about an effect of a school predictor? Could it be fixed effect? Sure. Could I have a random effect? The Zoomers are begging, please be done. 10 minutes, Zoomers, 10 minutes. Hang in there for 10 more minutes. What if I have effect of a school predictor? Could it vary over something else? Districts. Yep. So any level 2 predictors can have random slope variances over level 3, creating yet more variance components. And at this point, if I were writing a paper and my reader was going to have to keep track of like 7 different R squares, I'd be like, nope, total R square, the end. Just nope. So yeah, it gets complex, but you know all the concepts. It's just an order of complexity higher, quite literally, an order higher.
Lisa,
Yeah.
in the MSEM framework, how could we fit a 3-level model?
You can do it. There's 2 different betweens. In the syntax, you have to put a clustering variable name within the between to tell it if it's level 2 or level 3.
Okay,
I have examples of M+ code if you want.
great.
But yeah, you could do this as a multivariate model where X would get 3 levels of variance figured out, Y would get 3 levels of variance figured out, and you could throw in whatever fixed and random slopes you want.
Great.
And that would only be a 2-variable model, by the way. You think about it?
Exactly.
2
Yes.
things, 2
Yeah.
concepts. How many of you do research in which there's only 2 variables that you would ever care about at a time? Anyone? Nope. Yeah. So yeah, order of complexity builds quite quickly in 3-level models because everything that's measured at level 1 is also measured at level 2. Yeah, more words. Here's what a random slope model would look like in notation. So placeholder and random at level 2, fixed effects and random at level 3. Yeah, so this is within school predictor. What if I had just not within school centered this, cluster mean centered this, and just stuck in X? Can I do that? Smushed. How many kinds?
3.
Yeah, there's at least 2, right? Because if I put in, normally a smushed effect assumes the within and between are the same, right? But now I got 2 betweens. So it's assuming the same slope at all 3 levels if you smush it. And can you guess how I'd fix it? Unsmush it? How do I do that? Cluster means center? What'd you say? Centering, yep. Yep. Let me skip to that. Okay. It would look like this. And now you know why I'm calling it variable centering rather than cluster mean centering, because it generalizes. So let's say that I'm interested in examining the effect of teacher experience predicting teacher outcomes. So at level 1, if I have teachers within schools within districts, level 1 is the within school effect of teacher experience. I would subtract the school mean from the teacher score, and then this would be only level 1 information, right? That's what we did this semester. At level 2, though, I now have to also center that relative to 3. So I would take the school mean of teacher experience at level 2 and subtract from it the district mean at level 3. And then this new variable only has level 2 school info. It can only have the level 2 school. At level 3 then is the district mean minus whatever number it takes to make 0 mean something. And then this only has district information. So this model would give you within, between, essentially.
Does order of operation of calculating those things matter?
It does.
And so it's essentially start with level 1, subtract off level 2, then level 2.
Subtract, yeah.
Okay.
And I have a note in here. I had screwed this up at various points in my examples. You need to compute the level 3 mean using the level 1 variable, not the mean of the level 2 means. It doesn't, the unbalance will introduce correlation otherwise. So this is within, between, essentially is this. Can you guess the alternative? If you don't have a within, between type of model, what do you have instead? Oh, within contextual. How many different contextual effects can I have in a 3-level model? 2 of them. Too many, that is correct. But conceptually, if we think about it as the context effect is how different the within and between effects are, is the level 1 effect different than level 2? That's one context effect. And is 2 different than 3 is a second. But the same math works to stack it all back together again. Within plus contextual is between. Between minus within is contextual. You just have to keep track of your levels. So.
In that case, it would be within plus contextual to get it back, like to put it back together.
Yes, to get all the way back up to the highest between. Yep, so here's some equations that would show what this looks like that way. Here's the constant centered version, where once you have level 2 and 3 in the model, then level 2 is the contextual effect for the extra contribution of the school after controlling for the teacher. Level 3's contextual effect is the extra contribution of the district after controlling for the school and the teacher. So if I move schools from the same district, I'd add the level 2 part. If I move to a new district, I'd add the level 3 part. Same concepts. Chapter 11 in my book has time within student within classroom, I think. And it has a whole big long section about centering and all this stuff too. So there's a lot more words to be found there. Yeah, and here's some equations. All right. In example 8b that we're not going to do, don't worry, I'm not crazy. I'm just telling you I made it, okay? I have example 8b files here that took, do you remember the free and reduced lunch data? There were districts in that we ignored. Oops. Does that count as lying if I deliberately simplify so that I don't make your heads explode? No, I think that's just...
Not in a bad like morally,
Yeah.
yeah.
It's more of like a venial sin or something, like it's, it's like lying for a good reason. So yeah, I totally ignored district level 3 clustering in building example 4, and so I fixed it. So that's the same data. Spoiler alert, free and reduced lunch is a district variable. It is also a school variable. So you can, there's a lot of contextual effecty stuff happening in here, so you can take a look at those if you wish. Okay? There. See? Now I'm done. I don't want to do any more. I'm just done. See? The last slide ends with, phew, we made it. We're done. All right, 1:40, which means I have a few minutes for questions and comments if you have any.
Words of gratitude for all you've done this semester.
Well, thank you. I was going to do that back at you. Yeah, that's what I was going to end with, is a very sincere thank you. Honestly, I know you showed up, you did your work, you tried your best. Hopefully you learned some new things, or at least you have some resources to pull from when you need to do it in the future, which is when the real learning happens. There's real learning that happens once you run these models on data you care about. That's where the magical transition happens. Right, Vladimir? He's like, yeah, I hate this right now. But no, I am very grateful for all of you. It's been a pleasure. You have earned the right to bother me, okay? Having gone through this class, you have earned the right to remember my email address, and if you need help in the future, I can help you, okay? All right, thank you. I really appreciate it. Woot. Can we all clap it out?
Yeah.
Everyone gets a round of applause. We're going to clap it out. All right. I'm going to stick around for a few minutes in case anyone wants to talk to me. Otherwise, have a great break. Let me know if you need anything, and I hope to see as many of you as possible next year. Bye for the last time. 2023 out.